imagine that we've got the power series expansion for a function f. We're going to use T1 as our approximation. And then we want to be able to say something interesting about R1, about the error. So first of all, is sometimes the error is 0. Sometimes the error is 0. It's actually so what kind of functions do we have where f of x is exactly equal to f of 0 plus f prime of 0 times x? And remember, f of 0 is the y-intercept. F prime of 0 is the slope. So what kind of functions look like mx plus b? Linear, exactly. So exactly. So what makes a graph linear is there's no curve. It's completely flat. What calculus concept measures how much bendiness there is in the graph? Which derivative? Second. Right? Remember, the second derivative measures concavity. So if f double prime is almost 0, then the graph is almost a straight line. And if f double prime is significantly bigger than 0, then it's very bendy. So f double prime measures f. So we're trying to do is say something about the error using the T1 approximation. And one thing it's going to depend on is the value of the second derivative. The bigger the second derivative, the bendier the function, and the less it looks like a linear function. So here's the setup. Let's take e to the x. What's the second derivative of e to the x? And this just keeps getting bigger and bigger and bigger. So we're going to derive our error formula. We're going to predetermine a range of x's that we're going to pick from. So we're saying the error formula is only going to work if x's come from this predefined range. So here is the setup to the problem already. We're using T1 of those. For x in some range. And the traditional letter we use for that is d. And we're thinking of d as distance from the center. I'd probably use an r for the radius. So we're picking x values in the range from minus d to d. What you're going to do is you're going to look at every x value you might be using you might be plugging into the T1. You're going to calculate the second derivative of those. Then you're going to take you're going to let m be the biggest second derivative that you see in that range. Again, I'm going to set this up so I don't have to worry about absolute values. You have to be a little more, the idea is the same. You have to be a little more careful. And so what we have is f double prime of x is less than or equal to m. And T1 has an f prime with an f in it. So how do I go from f double prime to f prime? I integrate. So watch this. I'm going to integrate both of these from 0 to x. This is something that doesn't bother the engineers, but the mathematicians is bothered. I'm with the mathematicians on this one. It's, do you see that we're using the same variable to stand for two different things? So what we're going to do is the integral from 0 to 1 of 3d squared dt is the same as the integral from 0 to 1 of 3x squared dx. It doesn't matter what we call the variable on the inside. So I'm going to change this to 0 to x, f double prime of t dt. Put that here. What's the antiderivative of f double prime? F prime. And what's the antiderivative of m? So with a careful integration, I got that f prime of x minus f prime of 0 is less than or equal to mx. My T1 has an f prime in it. I'm happy that showed up. It also has an f in it. So I'm going to do the same trick again. Integrate from 0 to x. Both sides. Looks weird with all those x's. Change the x's to t's. Go around here. I'll clean up over here. The antiderivative of f prime is f. I've got f prime or f of t minus, and this f of 0 is a constant. So that's f of 0 times t. 0 to x. I think it's f prime of 0.